Hi, I'm Sujin from Georgia Tech, and today I'll present our work, Principles and Methodologies for Serial Performance Optimization. Performance has always been a central goal in systems research. We care about latency, we care about throughput, and that's especially true here at OSDI. Over the past 10 years, 43% of all OSDI and SOSP papers were about performance. And how do I know that? Well, yes, we actually reviewed all of them. Before we dive in, let me briefly set the context of this work. This is not a paper building a new system. It's more like a survey or really a systematization of knowledge. So we asked a meta question, can we systematize how sequential performance is optimized in practice? To answer that, we reviewed 477 papers from the last decade of OSDI and SOSP. And from there, we distilled a unified framework of recurring optimization patterns. So this is not a one-shot solution, but it's more like a practical guide, a tool to help you find the right solution for your own system. Let's say you're scaling up your system. You add more threads, and performance goes up just as expected. But then it suddenly drops. So you start profiling to figure out why it happens. It's not memory, not I/O. You got it. It's lock contention. And you see that threads are waiting too long to grab a lock. But now you're stuck with a classic question. What can you actually do about it? How do you optimize this? Parallelism is usually the first thing we can try. And yes, as you add more threads, performance increases, but only up to a point. Amda reminds us your speedup is limited by the part that stays sequential. No matter how many threads you throw at it, that sequential portion becomes the bottleneck. And that's where this talk begins. To bring up your memory, let's look at what's really happening when we hit lock contention. We have multiple threads running concurrently. That's fine at first. But as soon as they need to enter a critical section, they're stuck. Only one thread can go through at a time. So now threads are queued up, waiting, and that waiting is sequential. This becomes the bottleneck. Of course, you might try to increase parallel access in different ways, something like sharding, lock splitting, maybe fine-grained locking, but at some point, you hit a wall. Some parts just cannot be parallelized any further. And that's why sequential optimization remains crucial, even in this parallel world. Naturally, people have tried to optimize this sequential part for better throughput. Some systems try to reorder the queue so that short or critical threads can go first, and others batch similar threads to take better advantage of shared cache. And some let the application provide dynamic reordering policies. These are all clever ideas, and they work, but they are developed in isolation. There is no shared structure or language that connects them. So each time, we invent a solution based on our experience and explain why it works, and it's hard to know what else we might be missing. And actually, there are already dozens of techniques out there: caching, buffering, prefetching, and many more. They're used all over the place in systems, but in many cases, they're simply passed down informally from one generation to the next. They feel scattered. There's no shared vocabulary, no structure, and honestly, there was no clear picture of how many meaningful approaches are out there. We asked 3 questions. First, can we systematize this space? Second, how many distinct approaches really exist? And third, when should we use each of them? Overall, we want to create a systematic guide, something you can actually use when you're stuck on a performance bottleneck. Speaking of sequential performance, we realized that all optimizations boil down to just 3 core principles. Instead of giving formal definition today, let's keep it intuitive. So first, you can remove a task. If something is redundant or unnecessary, you can skip it. Second, you can replace it with something faster, maybe a more efficient version or even an approximation. Third, you can reorder tasks to improve locality or reduce overhead. Sometimes just changing the order leads to better performance due to hardware characteristics and locality. That's it. Remove, replace, and reorder. Every sequential optimization can fit into one of these 3 buckets. And from those 3 principles, we identified 8 common methodologies that show up again and again in real systems. Things like batching, caching, precomputing, deferring, and many more. Now, many of these may look familiar to you, and that's the point. We didn't invent them. We found them by analyzing the last decade of OSDI and SOSP papers. What we did was to organize them. We turned scattered ideas into one unified framework that helps us reason about sequential performance. Each of these 8 methods is directly derived from the 3 principles of remove, replace, and reorder, and that connection gives us a clear way to understand the rationale behind each methodology. This framework helps us understand which direction we are taking and which approaches we might be missing. What used to be an open-ended, intuition-driven process can now be approached in a clear and structured way. So, are these 8 methodologies enough to cover what people actually do? To answer that, we manually reviewed every OSDI and SOSP paper published over the past 10 years, and that's for 77 papers in total. And out of those, 206 focused on performance optimization. And surprisingly, across those 206 papers, every optimization technique we found fit into one or more of the 8 categories. Now, we are not claiming that these 8 cover all possible potential techniques that might come up in the future. That will be very difficult or maybe impossible to prove. But these 8 methodologies can cover every pattern we have seen in practice over the last decade. And we believe that's enough to be useful. This chart shows how frequently each methodology appears. And it really reflects what real system papers have actually been doing over the past decade. Yeah, instead of working through all 8 methodologies today, I'll just cover 3 of those. Let's start with the most familiar one, batching. In this example, we are starting with a sequence of tasks, and instead of handling task B, D, and F one by one, we group them into a single task G. As a result, we end up with fewer tasks overall, and the batched task is shorter than the sum of its parts. So when does batching help? First, it coalesces repeated calls that each have high overhead, such as logging, system calls, or network requests. Second, it helps you discard stale tasks. Once tasks are grouped together, you often realize some of them are no longer needed, like in group commits or write buffers. And third, batching improves spatial and temporal locality, which helps with cache and memory performance. And as you can see, batching is really a combination of remove, replace, and reorder. Let's look at another one, deferring. Deferring is simple. Instead of doing something right now, you push it to later. Ideally, when it's cheaper, less disruptive, or when you have more information. There are 2 main ways this helps. First, you can move tasks out of the performance-critical path. Deferring a task doesn't always make it faster, but by taking it out of the main sequence, you reduce pressure on the hot path and use idle resources later. In this example, tasks A, C, and E are pushed out of the main sequence, reducing the number of tasks in the sequence. Second, you can reorder tasks within a sequence to improve performance. By moving certain operations later, you might reduce stalls, improve locality, or make better use of future data. Both techniques rely on speculation. Sometimes you delay a task, hoping it might not be needed after all. Other times, you wait because doing it later could be more efficient, like deferring on a location or delaying a flush. If the speculation is wrong, performance might suffer, so good speculation is often the key to effective optimization. Let's look at the last example, contextualization. This technique is about making smarter decisions by using runtime context. Here's what happens. We insert a new task, G, to collect information about what's happening in the system. That might include things like memory pressure, request patterns, or workload types. Now, using that context, we can improve the decisions that come afterward. For example, we might decide which data to swap out or choose a better time to run a maintenance task. Of course, inserting G adds some overhead, so this only makes sense if the later optimizations give us a bigger win than the cost of collecting the context. And if the analysis can be done out of the main path, we can often move it off the critical path to further reduce the overhead. In our paper, we covered all 8 methodologies in this way, showing definition, visualization, real examples, and when to use it. Let me show you a quick example of how our framework can help in practice. To make things easier, let's revisit the lock contention scenario we saw earlier. Syncrd from OSDI 22 improves this lock behavior using several techniques. To maximize the throughput, Syncrd allows the lock to reorder threads in the queue instead of just following strict first come, first serve. We analyzed the ideas behind Syncrd through our framework, and they map directly to those methodologies we covered. First, deferring. If a thread like T2 holds the lock for a long time, Syncrd delays its execution to reduce its impact on overall throughput. Second, contextualization. So to make that decision, Syncrd collects runtime context, such as how long each thread held the lock. And third, batching. Threads on the same socket are grouped together to improve locality and better utilize NUMA memory. And now here's the fun part. We used our framework to explore further optimizations that were not used in the original paper. We found 2 additional opportunities. First, we applied caching by storing additional metadata in per-thread cache lines, and this improved throughput by over 23%. Second, we used delayering, which means running verified policy code directly without extra indirection, and that gave us another 14% boost. Our framework goes beyond analyzing existing techniques. It let us uncover overlooked opportunities by thinking in a more structured way, and that leads to real performance improvements. To wrap up, sequential tasks are the fundamental building blocks of performance optimization. And we propose a systematic framework to guide this sequential optimization. For humans, we published a performance manual, which is web-friendly form of our paper for easier access. And for those who want something more automated, we also built SysGPT that takes your problem and suggests optimization ideas based on the 8 methodologies. What's cool is, even though it was not trained on the most recent papers, this SysGPT can really capture ideas from them. So whether you prefer reading or asking when you're stuck on a bottleneck next time, we hope these tools give you a starting point or a more structured way to think. Thanks for listening, and I'm happy to take any questions.